Hello. So in this chapter, we're going to be looking at vectors. And so in this first part of the chapter, we're going to start looking at, I guess, some fundamentals, right, to do with vectors. Most of it will be a GCSE recap, but we'll be probably looking at it a bit more greater detail. But it's good to recap anyway. Right. Okay. So vectors then. Now, first and foremost. You probably would have seen this before, but a vector is basically something, is a quantity that has both a length, right, or size, right, both length and a direction. So what do I mean by that then? Right, so picture this example. Let's say I'm in the middle somewhere, right? Someone's just in the middle, and then they walk, say, 10 meters forwards, right? And then they end up there, right? Obviously, what we call that then, if they walk 10 meters forward, the distance would be 10, right? Or 10 meters, right? I hope so. That's just how far they travelled, right? The distance they covered. Okay, but what about instead then they walked backwards by 10 meters, and then they ended up, say, over here, right, at 10 meters, right? Well, the distance would still be 10, right? However, obviously the direction exactly where they went, forwards or backwards, that's different, right? So we went 10 meters forward here, and on the left we went 10 meters backwards. So how do we sort of encapsulate that then? This notion of a direction. So obviously the distance is the same, but in one case they went forward and in the other case they went backwards. This is where vectors come in, which specifies, as well as a length or a size, in this case the distance of 10, there's also a direction. And you would have seen this in mechanics, but I'll touch on it now in case you haven't seen it. But the distance is the length of 10, but then the vector version is what we call the displacement. Now, like with the, like the XY axis, right? X is positive on the right side, right? And then on the left side, it's negative, right? On the negative x-axis. It's the same idea here. It's the same idea. So because they're going forwards, this is like the positive direction, which means the displacement is positive. So that will also be 10, right? So the displacement is the same as distance because the length is 10 and it's in the positive direction, so it's 10. However, in this case, we're going backwards. Now, like the x-axis, right, you're going to the left, you go in negative. So this is the negative direction, right? So we're going backwards. That means the displacement then is what we call negative 10 then, okay? For the negative sign to give that distance, to give that direction as well, meaning it's going in the negative direction, okay? So that's what we mean by a vector being have a length and a direction. The displacement is a vector, okay? I'll make a note of that. You would see this in mechanics if you haven't already. This is a brief sort of introduction. So displacement is a vector, whilst distance is what we call, well, the distance is the length, right? But technically we call that a scalar, okay? So a scalar is literally just the length part of it, right? Just a number, right? But the problem is the distance doesn't encapsulate or consider the direction as well, just literally the number of how far they travelled. Displacement is the vector where it can be positive or negative, meaning it could go forwards or positive, but also if it goes backwards then it'd be negative. So it adds that direction part of it as well. That is what a vector is, plain and simple. It encapsulates the length, in this case how far they go, but also where they go. So is it positive or negative? So is it forwards or backwards? And that is simply the idea of a vector. Okay, cool. So the next thing we need to talk about are parallel vectors, which again, hopefully you'll be comfortable with from GCSE. Right, so let's just consider a vector, right? Let's draw, which is basically just a line, right? An A. And this arrow here, by the way, this arrow means the direction, so it's going up the line in that way. And the vector we'll call A. Now we write our vectors with the letter, right? But usually, obviously, we make it bold if we're on the computer, but if we're handwriting it, obviously we've got to do bold writing on hand. So we do an underline in that way. Okay, or you might see an arrow above it. Okay, either or, I'm going to underline it in this way. So this is the vector A, right? So it's telling me the direction is in fact that line, right, going up, and that's the direction, and the length will basically be the length of the line, right? Which actually we know to calculate, right? You know, the length of the line, it's the distance between the point at the end there and the point at the end there. We'll look at more about distances later on in the chapter, but that's the idea, right? So the direction is, you know, it is represented by the arrow, meaning it's going up the line in that way, and the distance or the length of the vector is the distance of the line, right? Basically, right. Now, also because of that, because it resembles basically a line, well, what do we know about, you know, lines and, you know, the direction? It's about gradients, isn't it? Right, the gradient is basically telling us where, like the line, how far the line's going, right? So you can kind of think about a vector drawn this way, sort of like comparable to a gradient of the line, right, which is the direction. With that in mind then, think about parallel lines then, right? Two parallel lines have the same gradient, right? Roughly something like that, right? Oh, let me draw it again. There we are, roughly like that. So hopefully you can notice they have sort of the same parallel lines, right? That's what I'm getting at. These two lines or vectors are parallel, right? So again, you can think of it as, again, like parallel lines have the same gradient, and that usually means they don't meet then as a result. So that's what we, when we looked at straight lines in chapter 5, that's what we mean by parallel, like the same sort of gradient. We can sort of encapsulate that here with vectors as well. So two vectors are parallel if sort of their direction is the same, right? Remember, direction is basically gradient of a line. So the directions of two vectors have to be the same for them to be parallel, right? So this is vector B then. Then we could say A and B, the vectors A and B are parallel because they have the same sort of direction, right? Which means they basically never meet. Right. So you might be inclined to then say, well, really, A equals B, right? Because the direction is the same. But what if instead we kind of extended the second line like this? Well, the same. It's the same direction this time. You know, the direction's not changed. Like the arrow, the slope of the gradient of the line hasn't changed, but have changed. Well, it looks like. Let me draw that a bit more accurately. There we are. But you can see the length has changed, not the direction or the gradient of the line or the vector, but the length has changed. Right, I've extended the line, so hopefully you can see it's far bigger now than A. So this doesn't make sense anymore. The gradient, the vector A can't be equal to vector B because they're not the same, because the length isn't the same. So basically, but you can spot the direction is the same, right? So therefore they're still parallel because like with lines, two lines are parallel, same gradient, right? But the length can be different. So this doesn't really make sense anymore, equaling each other, because obviously they're not equal because the lengths are different, but the direction or the gradient is the same. That's the key idea, right, to be parallel. How we can then represent this is actually we can say that instead of just being equal to each other, we can say two vectors are multiples of each other, right? This multiple k, right? So k is a multiple, okay? So that means then this k means, for example, say if this b was actually two lots of a, then we can say, but obviously they're going to be parallel then, so we can say that 2a is twice lots of a. In other words, the second line here, or the vector here on the right, is double the vector on the left. But they're still parallel, because it's the same gradient. They're the same gradient at the end of the day. So that means that we just need to be, two vectors are parallel if they're just multiples of each other, right? But this multiple only accounts for the length, right? If I'm doubling the vector, I'm not changing the direction, I'm just extending the line, right? So I might change the length of a vector, but not the gradient or the direction, okay? And so basically this is what we mean by parallel vector then. So I'm going to then say two vectors AB are parallel to each other if we can express or write vector A as a multiple of vector B, okay? Where K is what we like to call scalar, okay? So scalar just means a number, right, essentially. It's a fancy name for a number, okay? So K is just our multiple, okay? So two vectors are multiple of each other, which means therefore they're parallel, because they might not have the same length, like in this example, but they have the same direction, okay? The same direction means they're parallel, okay? So that's the key here. So that's what we mean by parallel, okay? You need to recognise pretty much quickly, immediately, if two vectors are multiples of each other, then they're parallel. And we can prove two vectors are parallel by making them multiples of each other, okay? We'll see more examples like this later on in this video, but that's that for parallel vectors. The whole, you can kind of think of it as lines, right? Parallel lines. You know, there might be... the whole essence is that the direction is the same, or the gradient is the same. Right, okay. Okay. So the last thing we're going to look at, which probably you wouldn't have seen, is this idea about a triangle and a parallelogram law of adding vectors. Right. So let's start with this triangle law of adding vectors. So what's going on here then? What am I talking about here? Well, if I have any two vectors, let's say I have vector A again here and vector B, say, is here. Then if we add these two vectors, which we represent by A add B, then we basically start with vector A. So it would look like this again. So it would look like that. So we started here, and then obviously we move up the line, and then we end up there. So then we end here, and then we add the vector B afterwards, as so, okay? And then obviously we end up there, right? So hopefully you recognise that we're starting here. So I'll say start, and then B is the end there, right? So the end there. Well, actually then, hopefully you recognise we can sort of make a triangle, right, between these two vectors. We can call that vector C, okay? And actually then, when we're doing A and B, so we're going along A, right, first of all, we're going along A, and then we're going along B, and then we end, so we start here, and then we end there when we go through vector A and then go through vector B. But actually, we can then make another vector C, which actually directly goes from the start to the end, right? Without having to go through two different vectors. If we add in two vectors, we can get to the start to the end between those two vectors by just one vector. So we can then say that this A and B equals C, okay? So the whole idea is then, in words, is if we have two vectors, A and B, if we add them, So we get A and B. Then there's a vector C with obviously with A and B equals C. Okay, and that's really it, right? So that essentially we can and we can make a triangle. And we can make a triangle with vectors A, B, C. Okay, so the whole essence is if we have any two vectors, A and B, any two whatsoever, if we add them together in this way, then then that total, right, gets me another vector C, which starts at the same point and ends at the end of the second vector, right? And that's the triangle law. Okay. Right, so then lastly, and this will be when we look at position vectors later on in this chapter, you'll really see this in action there. Okay, so this will make a lot more sense when we go along the chapter. But that's basically the whole idea of a triangle, right? We have two vectors, then we can add them, and then we get a triangle out of them, right? In this way. Right, the last bit is what we call the parallelogram law of adding vectors. So you probably guess then, with triangle law, we made a triangle. Now the parallelogram, we're going to make a parallelogram out of vectors. So again, we're going to consider two vectors A and B. And so with this law then, if we have a vector, say A, again, and then we have a vector, say B, B, say there. Well, in this case, instead of just adding B after A, right, so instead of just going A and then B that way, and then adding A and B to get obviously the triangle A and B, we're going to find their total, right, in a different sort of way. Instead of them being one after another, so A and B, we're going to make them adjacent to each other instead, okay, in this way here, right, B. And so actually then we can make a parallelogram out of two vectors, right? When we make two vectors adjacent in this way, so they meet at a point there and they both go off that point. If we can make a parallelogram, right? So then if we have this line, I'll do it dotted, this one. If we can make the side, that will be parallel to B, so that would also be B. And that'd be the same length, so it will be exactly B. And we can make the opposite side to A, and that would also be A. Okay, so we make a parallelogram, right? In this way, when we make two vectors adjacent to each other in this way, we can form a parallelogram, right? So the opposite sides will also be that same vectors. Okay, and so what that means is then actually, moreover, the diagonal here, the diagonal, if we call that vector C, then, well, actually, to get from the start here, then to get to the end here, then, which is vector C, we can actually go along. If I do it in red, actually, I don't have red. Okay, let's do pink. So if I go along, so to get to C, if I find that vector C, then the diagonal, I can alternatively, if I start here, I can go at A, and then go to this B, there, and then we end there. Okay, so then we can also say that the C is then going to be A and B. Let me do that. I'll leave it in pink. So C is A and B, and we can get the total of A and B that way. So that's what we mean by adding vectors. If we have two vectors A and B, we can add them alternatively in this way by forming a parallelogram. Okay, and that's essentially it, right? So instead of just adding a vector A and then adding on the vector B, to then form a triangle of A and B, I can instead form a parallelogram by making them adjacent, okay, instead, okay? So again, we had vector A there, and then a vector B there. So now they're adjacent. They're not one after another, but then we can form a parallelogram, okay? And so the diagonal is their total. So that the diagonal would be A and B, which we can call vector C, okay? So that's the whole idea, right? So it gives these two laws, the parallelogram and the triangle law, give me two different ways of visualizing what adding two vectors means, okay? So I guess in words then, in the parallelogram, is if we have two adjacent vectors AB, which basically again means they basically go off, if they meet at a point, they go off right from that point, okay? That's what that means. So we have two adjacent vectors A and B, then we can construct a parallelogram with these sides, with these vectors as the sides. And moreover, the diagonal is the sum A and B, okay? So the diagonal represents the addition of those two vectors, okay? So if I want to add the two vectors together, I can then do the diagonal of the parallelogram, okay? And actually, the parallelogram law actually is also really equivalent to the triangle law, because consider this: if we have our two vectors then, A and B, obviously they're away from each other now. Obviously they are adjacent, right? So they're facing away. Obviously we construct our parallelogram, right? That's what the parallelogram law tells us. We can construct the parallel vectors this way. And then obviously the diagonal there, as we've seen, is A and B. But actually then, if we just take away that side A and then this top side B, well then we got the triangle law, haven't we? This is now the triangle law of addition. So actually the parallelogram law is basically kind of exploiting the triangle law, right? But we get a parallelogram. But yeah, so that is basically the essence of these two sort of laws, right? They give us different ways of basically adding two vectors, right? At the end of the day, this is how we can add two vectors together. Now, I haven't seen any exam questions where they directly reference or ask about the parallelogram or triangle law, but obviously implicitly you will be using these laws throughout the chapter when you add two vectors. Implicitly in the background, that's what you'll be doing. That's how we add two vectors, via these laws. But yeah, but obviously, as the specification says, if I get it up here, you do need to be aware of the triangle and the parallelogram laws. So hopefully you can kind of understand that. As again, these two laws give us basically the way of basically adding two vectors together. Hopefully geometrically you can see that by the diagrams I've done. But that's what these laws are doing, is basically giving a way to add two vectors together. Right? But yeah, so we'll move on to some examples now. Okay, so we got this question then to start with. We are given a diagram with vectors A, B and C on a square piece of paper. We need to draw a diagram to illustrate the vector addition A and B and C. So that means then, well, we're going to start with A. Now, we have to pay attention. A, we can consider the direction as changing X and changing Y, just like the gradient Y, right? So we go, how many squares across? So we start here and end there. So we go 1, So we go 1, 2, 3, 4, 5, 6 across, and then 1, 2, 3 up. So basically, the direction of the vector A means we need to, let's say we start here. We need to go 6 boxes across. So that'd be 1, 2, 3, 4, 5, 6, and then 3 up. 1, 2, 3, and there we are. So then we construct the line between those 2 points, and there we are. So that's vector A. Then we need to add vector B. So then we're going to, at the end of A here, then we're going to start and we're going to add B onto it from that point. So B, then we're going to do the same. So this is B. So again, we're going to start here and end there. So we're going to go 1, 2, 3 across, and then 1, 2 down. Okay. So with that in mind, we're going to go 3 across. So 1, 2, 3. And then 2 down, 1, 2, there, okay? And so therefore, if we connect the two, I get that vector B there. By the way, you can do it in, I'd recommend doing it in pencil, and then obviously once you've got the final thing, then do it in pen. But I've not seen an exam question with this example, but either way, that's B. Then lastly, we need the vector C, so that's just straight down. So that is how many down? 1, 2, 3, 4, 5 down, okay? That's 5 boxes down. So then we just need to go 5 down there. 1, 2, 3, 4, 5. And then we end up there. So the vector C will be there. And that's where we end up with, okay? That's where we end up. So overall then, this that represents A, B and C. But actually, notice I can just draw a single vector between the start of A and the end of C. Very similar to the triangle law, but instead of 2 vectors, I've got 3. And so actually, wouldn't that just be A and B and C? That is the vector A, B and C on the diagram, okay? So we can add multiple vectors in this way with a diagram by just drawing the line at the start of one vector, and then we go along and the end of the last vector, okay? And so there we are, A and B and C. That's very similar to the triangle law, okay? But obviously we've got, instead of 2 vectors, we have 3. Right, so we have this question then, and it's a GCSE style question, really. Again, so in A level as well, you may be expected to work out different paths or different vectors of, you know, on a diagram like this. But we'll work through this example. I noted here also, if we want to go reverse the direction of a vector, we do the negative of it. So for example, if you had a vector A, right, that goes up the line like this, we can reverse the direction. So it would look like this, but it would go the opposite way, and that'd be minus A, okay? So we can go the opposite way by doing the negative, okay? Because remember, the vector has direction, so going up or going forwards or backwards changes the sign of it, okay? Just like when we looked at the displacement distance example at the start of the video. Okay, so with that in mind then, we first need to find, so they've added the vectors on the diagram, we need to find firstly the vector PS, and we read that as the vector from P to S, okay? So basically we want to find, what this essentially means is we want to find the path from P, which is here, to S, which is there, okay? Well, obviously that's the vector, right, from P to S directly, but it's not labelled exactly in terms of the vectors A, B and C and D, what that is. So we need to find, and the whole idea of these questions is to find a different path to end up at that point, okay? So we can't go from P to S directly in that way. So let's think about, instead, we could actually go from P to Q in that way, and then Q to S, right? Hopefully you can see that, and then we end up at S. So the whole idea is we start at P and end at S, and that's what we've done here. But instead we had to find a different route, which instead we went from P to Q, and then Q to S. Okay, cool. And now we have vectors for those. P to Q, well, here, well, from Q to P, so it's going that way, that's A. But we want to go the other way and go up. So P to Q instead. So actually that would then be negative of A, because remember, like we just said, going the opposite direction, we need to make it negative. So with that in mind, it's going to be minus A instead, and then Q to S, it's just C, okay? The vector C, and that's it. There we are. Right, part B then is R to P. So we want to start at R, which should be here, and end up at P there. Now obviously you would just go along this line here to get directly from R to P, but we can't do that because we don't have a vector for it. So we need to find another way. And actually I can go from R to Q that way, and then from Q to P that way. So I could say that's R to Q and then Q to P. Okay. Now again, so Q to R, well, I know this way is B, right? That is B, but I want to go the other way, that way instead. So I need to do the negative of B. Okay, and then Q to P along there, it's just A, right? So add A, and there's my vector. Cool. Part C then, we need to find P to T. So we start at P and end at T. Well, obviously the direct vector would be that. The direct vector will be there, but obviously we don't have a vector for that, so we need to find another way of getting from P to Q to T. Well, I can go along this way, so I can go from P to Q, and then Q to R, and then R to T. And there we are, I end up at T. And that would then be the vectors P to Q, add Q to R, add R to T. Okay, and there we are. But so then P to Q, well, again, likewise in part A, that way is A, but I want to go forwards instead. That would therefore have to be minus A because I'm reversing the direction. So that'd be minus A from there. What about here? From Q to R, that would just be B, right? And then R to T would be D. And there we are. Cool. Then lastly, I need T to S. So T to S, obviously we start at T, end at S. So obviously the direct vector would be there, but as always, it's not that simple because there's no vector there. So I need to find another way of going from T to S. And I notice along the, so I need to find the path that I know the vectors for. So it's probably best to start from T to R then. And then I can go from R to Q. And then I can go from Q to S. And therefore I end up at S. So that could be my vector then. So it could be from T to R, and then R to Q, and then Q to S. And there we are. Right. Well, T to R then, well, that way is D. Which, by the way, that's what the arrowhead there means. That's the direction of the vector. So, but I want to go the other way. So I have to reverse that, and instead of D, it'd be minus D. Okay, then R to Q up there, well, again, that way is B, but I want to go upwards instead, so that'd be negative B. And then lastly, I need to go to Q to S, and then that vector is C, so that's just C. And there we are. So that's the whole gist, right? Exactly like GCSE, I can find different paths in that way by considering multiple different vectors. So I want to find a path that starts at one point, say P. So for PS here, a path that starts at P and ends at S. I need to find perhaps a different route instead of just P to S, so I can combine different vectors together like this and add them together. Okay, and that's the whole strategy, right? And then there we are. Cool. Right. Right, we have a more of a step up of a question here now. So we're told in triangle ABC here, AB is A. So I would say that A would be there, right? A is there, right? So along AB, if I draw my arrow, A, that's the vector A. And AC, so from A to C, that is B. So that line there is B. Right, okay. I'm then told, and this is why it's a bit harder, P is the midpoint of AB. Now, don't get freaked out about seeing stuff like this or ratios, but just think about midpoint, right? Midpoint, you know, is just halfway along the line. So if the overall line, and let me draw a bigger triangle actually. So A is there, then C is there, then B would be there, and capital B, and there we are. And we have P in the middle there. And then we have Q somewhere there. But overall, the vector is A, right? But if P is in the midpoint of AB, then that means we can actually split up A to P to be a half of A, right? And likewise, the other half from P to B, okay? So we can split up the line AB into two halves. That's what P's doing, okay? Likewise, we have Q, which divides AC or splits up AC in the ratio 3 to 2. Now, with these ratio questions, again, don't be too caught up in it. But when we have 3 to 2, then that's saying that the first part from A to Q is 3 parts, and then from Q to C to the other part of the line is 2 parts. Well, overall, we know that it's 5 parts then, right? And we know overall, as you can see here, the length of AC is B. So if you want 3, so B, right, represents 5 parts, right? So if we want to get 3 parts, we'd have to we'd have to divide by 5 to get a fifth B is 1 part, and then times by 3 to get 3/5 B is 3 parts, which means that therefore as a vector we can say that the first from A to Q, right, the 3 parts of the line, that's 3/5 of B, okay, and Q to C would then be 2/5 of B, and that's really it, right? And obviously, when you get more comfortable, you don't even need to do this sort of ratio stuff, right? Hopefully, you should be able to immediately spot. Well, if Q is splits AC into 3 to 2, well, that means it's going to be 3/5 of AC. So we would say A to Q is 3/5 of AC, but AC, you know, is B, so it would be 3/5 of B. Okay, which we got there. But anyway, there we are. So we've fully labelled our diagram now. Now, it says write in terms of A and B, firstly, B to C. So again, we want to start at B and end at C. So we want this vector here. Okay, well, obviously there's no actual directly from B to C. There is no vector there, right? So we need to find another path to end at B, start at B, end at C. Well, we can go along here, right? We can go from B to A, and then we can go from A to C, right? So then we could say A to B, B to A, sorry, and A to C. Right, well, B to A, we know overall, right, from B to A, that direction, that way is A, right? But I want to go the other way. I want to go up from B to A. So I have to reverse that A to be a negative A. Okay. And then I then end at A to C. So well, that's just vector B then, right? And there we are. Cool. Right. Hang on. There we are. Right, okay. Just try to label it a bit clearer. Okay, part B then. We need to find A to P. So now we're going to start at A and we need to end at P. Well, actually, we already worked that out, really, when we labelled the diagram. A to P, we discussed, right? If P is the midpoint of AB, the A to P is going to be halfway of AB, right? So the line A to B is there. P's in the middle there, right? So it's going to be halfway, right? Well, AB then. AB is A, right? AB is A. So it's going to be half of A. And that's really it, right? Which hence how we got half A there. Okay. Part C then, we then need to find A to Q. So that's going to be starting at A and then we're going to end at Q there. Well, actually, we did that as well, really. Just that would be 3/5 B. But again, that's because Q divides AC in the ratio of 3:2. That means that A to Q, right, is 3 parts and Q to C is 2 parts. So AQ overall is going to be 3/5 of the whole line AC. Well, then AC, again, AC is B, right? AC is B, so it's going to be 3/5 of B. And there we are. Then part D, we need P to Q. Right? So P to Q then, this time, we'll be starting at P and ending at Q. Well, actually, we can go, you can take there's 2 ways really, but actually I spot, to get from P to Q, I can go from P to A, up there, and then I can go from A to Q, right? So I can say I can go from P to A, add A to Q, right? Now P to A then, well, that direction A to P is a half A, but I want to go from P to A. I want to go the opposite way. I want to go that way instead. So I need to do a negative of a half A, right? If I'm reversing the direction. So minus a half A. And then A to Q, well, we worked that out in part C. So it's just going to be 3/5 of B. And there we are. Okay, we can't simplify that anymore. But there we are. Right, okay. So I do know from GCSE, I've seen some students really freak out when they see stuff about midpoints and ratios and vectors. Please don't be disheartened or discouraged. Just recognise you can split the line up. If it's a midpoint, it'd be half of the line. If it's the ratio, consider the total, right? So the total would be 5, and then the first part will be 3/5, and the second part will be 2/5. That's all it is, essentially. And then from there, it's just the vectors we've already seen, okay? By finding different paths to get to 2 points. Okay. Now we're going to revisit our parallel vectors stuff. So in this example, we need to show that the vector 6a and 8b, so 6a add 8b, and 9a add 12b are parallel. So remember last time we said that 2 vectors, a and b, I'm going to call them c and d. Right, c, d are parallel if we can express them as multiples. So if we can say that vector C is multiple of vector D, where K is the multiplier, right, the multiple. So in this case, we want to show that these 2 vectors are parallel, 6a, 8b, and 9a and 12b. If they're parallel, they need to be multiples of each other. Well, then, let's think about it then. 6a then, would have to be some multiple of 9a. So basically the components have to be corresponding. So let's consider the a part first. Well, from get to 6a to 9a, I'm gonna basically then 6 is gonna equal 9k, right? almost like cancelling out the A's, right? Almost like that. But that means 6 is going to be 9 lots of k. Therefore, k is going to be 6/9, which will simplify to 2/3. That tells me then that this first vector is perhaps going to then equal 2/3 of that vector, right? We can expand this out then. So then we can say that 2/3 of 9a and 12b, if we expand that out, well, 9a times 2/3, that's going to be 9 times 2/3 a, and then 9, and then 2/3 times 12 lots of b, right? Well, 9 times 2/3 is 6, as we just saw. So that's 6a. Then 2/3 of 12, that's going to be 8, right? Well, hang on, we've got 8b there. So therefore, what we can then say is that therefore, the vector 6a and 8b is going to be 2/3 of the vector 9a and 12b. Oh. Well then, hang on then. They have to be parallel because they're a multiple of each other. They're a multiple of 2/3 to be exact. So therefore, the two vectors are parallel since they are what we like to call scalar multiples of each other. Okay, basically meaning there's a multiple between them, in this case 2/3, but that's the reasoning we use here. Okay, so hopefully you can spot then that I can to get from 6a to get from 9a to 12b, I multiply 2/3 of that, and then I get that vector there. So they're multiples of each other, hence they have to be parallel. Okay, cool. Right, okay. And going back to our sort of shape vectors and shapes, right? We can also consider parallel vectors and shapes. Okay. So we are given ABCD is a parallelogram. AB is A. AD is B. We need to find A to C, which is going to be that vector there. Well, if they're a parallelogram, then that means that the opposite sides, think back to parallelograms, the opposite sides of a parallelogram are parallel, right? So AB, this side up here then, is also going to be the same vector A, okay? And then this side here from B to C is going to be parallel or the same as B then, right? And there we are. And so because we added these vectors on, we can now find a way of finding that diagonal AC. So therefore, to get from A to C, well, we can go to B, right? We can go from A to B, which is A. So I can say A to B firstly, and then we can go from B to C. And A to B is A, and B to C is just B, right? And there we are. So therefore the diagonal A to C, there, the diagonal is just A and B. Well, actually, this is actually the parallelogram law that you talked about, right? Because we have we have the vector A here, so AB. If I if I remind you, A to B, that's A. Then I have the vector B, and they're both adjacent, right? So this vector A is adjacent to vector B because they're both going off at the point there, right? They meet at a point there, and they're both going off in that way, but they're both adjacent. Well, then that means that, as we discussed, that we could create a parallelogram between them, and that would then be vector A, and this would be vector B, right? And moreover, the diagonal we said was the sum of the two vectors, so A and B. But that's just what we're showing here then, right? The diagonal A to C, which is the diagonal A to C, is the sum of the two vectors that we've got, A and B. So that's the parallelogram law in action there. Okay, so I'll make a note. parallelogram law of vector addition. That is that, okay? That's the parallelogram law of addition there, okay? Cool. Right, cool. Okay, let's have a look at some more exercise questions. So we are told here that the vectors 2 lots of A and K lots of B and 5A and 3B are parallel. So we are told they're parallel. That means then there has to be a multiple. I'm going to call it, I've already used K. So I'm going to say that this first vector is going to be N lots of the other vector then. Because remember, 2 vectors are parallel if they're multiples of each other. The N is the multiplier here. Right? So one vector is a multiple of another. I can then sort of expand it then. Write this bracket. So 2A and KB is going to be 5N lots of A and 3N lots of B. Okay? But then what I can do then is sort of what I call compare coefficients. So that means the first vector part A, so obviously these vectors have an A part and the B part. So the 2A parts, the components have to be the same. So therefore I can say that 2A has to then be 5NA of the other vector. But therefore I can then say then that 2 has to equal 5N. So therefore N is 2/5, right? There we are. I can then also compare the B coefficient, the B component of both vectors. So then that also means KB has to equal 3NB. And therefore, again, K then equals 3N. But we also know then that N is 2/5. So K is 3 lots of 2/5, which is 6/5. And there we are. That's my value of K there. Okay. Right. Okay. Now we got this question. This question here. We are given a quadrilateral OABC, the vertices, right? We're given OA is A, and OC is 3 lots of B, and OB, which is there, is A and 2B. Right? I'm going to draw this a bit bigger as well, just so you can really see. So OA there, AB there, BC there, and then there we are. So that's O, A, B, and C. And O to A again was A. The diagonal O to B was A and 2B. And O to C was 3B. And that's all we know. Okay, the first asked us to find, in terms of vectors A and B, the AB, that vector, from A to B, which is going to be that vector there, right? So I want to go there. Obviously, there's no vector there. There's no direct vector, right? We're not given the information. So we need to find another way of getting from A to B. Well, actually, I can go from A to O, and then I can go from O to B, and then I end up from A to B. So there we are. But again, AO, well, O to A is positive A, but I want to go the other way from A to O. So I need to negate it, so it'd be negative A. Then O to B, well, we're given O to B, right? O to B, that way is just A and 2B. And so then I can add the same vector. So then minus A and A is just 0A, so no A's, so we're left with 2B. And that is my vector. Cool. Then we need C to B, right? So now we need to start at C and end at B, so I need that vector there. Obviously there's no information given there, so I need to find another way of finding that. Let's take another route to get from C to B. Well, I can go from C to O, and then I can go from O to B. Cool. So then I can say I'm going to go to C to O and then O to B. If I do that then, well, C to O, well, O to C that way is 3B, but I need to go the other way. So it'd be negative 3B, right? And then from C to O, then I need to go from O to B. Well, that's, again, it's just going to be A add 2B. And then I can just add the B's together, right? So I'm going to get A, and then minus 3B add 2B be minus B. And there we are, that's my vector. Nice. Then for part B, I need to show that AB is parallel to OC. So firstly, AB, to recap, I found in here in the first part to be 2B. I'm also given that OC is 3B, right? Well, actually then, they're multiples of each other, right? 2B and 3B, they're just multiples of each other. I can say that 2B is going to be some lots of 3B, right? Well, to work out this K, I can then say that 2 is going to be 3K, right? And therefore, K is 2/3. So more specifically, I can say that therefore, AB is going to be 2/3 of OC. Cool, and therefore I can say AB is a scalar multiple of OC, so they're parallel. Right, so again, I'm just using the definition that if I have two vectors, say C and D, they're parallel if they're multiples of each other. So C is some multiple of D, okay? That's all I'm doing there, okay? I'm making a multiple out of the two vectors. Okay, there we are. Okay, we've got this final question then. So I'm now told I've got ABCD is a trapezium with AB parallel to DC and DC is 3AB. And then we're given some more information. Now, again, with this sort of geometric stuff, it's best to draw a diagram, right? I wouldn't even attempt to solve it without a diagram. So I've got ABCD. So if I have the point here A, then obviously a trapezium looks a bit like this, right? Right? So A is going to be the top part. So A is going to be there, then B there. And then the next point down here would be C. And then D would say be somewhere there, right? And then obviously there we are, we're back at A. So we've got our trapezium. Cool. Just a very, very brief note. The convention of how we label our shape matters. So some people may have said A and then maybe they would have put a C there and then the D and the B. That's not really correct. The ordering matters. So the way we order a shape is clockwise, okay? So if we label our point A there, then B has to be next, right? Because it's anti-clockwise. Then C, this point down here, would be C. And then once we turn around, obviously D would then be next because of the labelling. A has to come first, then B, then C, then D. It might be like a point that most people might take for granted, but I've really thought I'd make the effort to emphasise that, just in case. Or else you would get the wrong sort of answer if you label the shape incorrectly. Right, so ABCD is there. AB is parallel to DC. We can obviously see that there, which again confirms we've probably done our diagram correctly. And DC is 3 lots of AB. Again, we can see that here, DC is going to be clearly bigger than AB. I'm not too worried about the exact sort of like proportions of my sketch. It's just a sketch, it's not an accurate diagram. But I can see they're a bit bigger, like the bottom side and the top. Okay, I'm given that M divides DC such that DM to MC is 2 to 1. So M, right, so D to M then, so this point here, say M, D to M, that has to be 2/3 along the line D to C. So if I have point the M there, Then this is going to be sort of 2 parts then, from D to M. Then M to C will be the remaining 1 part. Hence the ratio there. Right? So that's all that means then. So with that in mind, there we are. We are also given that AB is A. Now actually, we know AB is A and DC is 3 lots of AB. So overall, D to C has to be 3A, right? And also, furthermore, I know that DM, like I said, is 2/3 of DC, the whole line DC. So DM would be, well, 2A then, right? Because DC is 3A, so 2/3 of 3A is indeed just 2A, okay? And this will mean the remaining part has to be A. And you can see that then there, because I split the M in this way. So I have 2A there, and then another A gets me 3A overall. But that's what the ratio means. So there we are. And that's really it. And also B to C is B, which is there. So we've got quite a lot of information there actually. Anyway, let's find some vectors then. So we need to find, firstly, A to M. So A to M, well, it's going to be that vector there, right? Directly A to M, but obviously we don't know what that is. We don't have information. But actually, can't I just then go along from A to B, then B to C, and then C to M, right? I can do that path, right? If I then do that, then, well, firstly A to B is just A. Then I have B to C, which should then be just B. And then C to M, well, we know that M to C is A, but we need to go the other way, from C to M. So it needs to be that way. So we need to negate it and do negative A instead. Well, A take away A would be 0, so I'm just left with B. Okay. Cool. Then I need to find B to D. So that's going to be that vector there. But again, obviously, there's no actual information to find that directly. So I need to find another route. Well, to get from B to D, I can do BC, then B to D, right? And C to D, sorry. There we are. Well, B to C again is just B. And then C to D, well, I know D to C that way is 3 lots of A overall, right? Overall. But I want to go the other way from C to D. So I want to go that way. So I need to make it negative 3A. And that's my vector. Cool. Then I need to find for part C, if I do it here then, M to B. So that's going to be M to B. It's going to be there. Well, to get from M to B, kind of do MC and then C to B, right? If I do that then, well, M to C, we can see is just A. And C to B, well, B to C is B there, but I want to go the opposite way from C to B. So it would have to be negative B. And there we are, that's my vector there. Then lastly, I need DA. So that's going to be, oh, that vector there, right, D to A, right? But obviously I can't find that. Well, alternatively, I can just go from D to C, C to B, and then B to A, right? And then I end up at A. So that would be D to C, B, CB, and then BA. Well, DC firstly, right? So DC there, well, it's just 3A, right? So that'd be 3A. Then I need to go from C to B. Well, again, B to C is positive B, so C to B the other way would be minus B. And then B to A. Well, we know that direction is A, right? From A to B, so B to A, the other way around has to be negative A, right? So then I can just collect the A terms to simplify. So 3A minus A is 2A minus B, and there we are. Okay, cool. So those are the I guess all the examples in this sort of intro to vectors. Hopefully most of it should be like GCSE style, hopefully, but we will look at more concepts later on in the chapter. But yeah, so that's vectors. But I'll see you next time.